Good evening, Lower Six. I hope you coped okay with the work which I set for you on Hooke's law and the extension of springs and wires on Tuesday night. So obviously I will try and get that homework marked and some feedback back to you. In the meantime, we're going to set you some more work on materials, which I'm going to put a deadline of Sunday on for you to complete. The next section of work is going to be two small sections. The first bit looking at the energy stored when you stretch a material. And secondly, we're going to define two terms, stress and strain, which we're going to be using next week. So first of all, the energy stored when you stretch an object. So we're already familiar with Hooke's law. So just to remind you, here's a spring. If we extend a spring, the force required to extend it is equal to a constant, the spring constant, times the extension. That's basically Hooke's law. Now, while you're extending the spring, you're doing work. You're all familiar with the GCSE equation, work done equals force times distance moved. Every time you move the end of the spring outwards a little bit, you're displacing it further out and you're applying a force to do that. But the force actually increases as you get further and further out. Okay, the force here is very small. As I extend the spring further and further, the force increases. So if you look at a graph of force against extension, you would have to integrate underneath that graph to work out the total work done, because each small increment of distance as you expand the spring, you'll be increasing the force a little bit. So it's not just a simple case of multiplying the force at the end times the extension. If you integrate underneath a graph of force against extension, you actually get a half times the force times the extension. So half times F times delta L would give you the total work done extending the spring to an extension of delta L. We call this the elastic potential energy, because you do the work on the spring to extend it. Obviously that energy has to go somewhere. It's then stored in the spring. Okay, when the spring is stretched, there is energy stored in it. I know that because if I let go, the spring bounces back. So that's what we mean by elastic potential energy. You may see it called strain energy in some reference books as well. Okay, one equation you may be familiar with from GCSE is a half times spring constant times delta L squared, or a half spring constant times x squared, depending on how you write the extension. That just comes from the same equation, a half times force times delta L. If you replace force with spring constant times extension, you get a half times k times delta L times delta L. So half k delta L squared. So that means you can, if you know the spring constant, all you have to know then is the extension, and you can work out what the energy required is to extend the spring to that extension. So that's an important formula to learn, but it's also one that's on the formula sheet as well. Now, in the case of a spring, if you do extend it and you do the work to get it stretched out to that extension, if you release the force, goes back to its original length. The amount of energy released when that happens is the same as the energy you put in, and you can actually see that on the graph of force against extension, because the spring will follow the same curve going back down to its original length. Now, we did mention in the last lesson that that's not the same thing for a different material. So here I've got a rubber balloon. And if I stretch a rubber balloon, it doesn't obey Hooke's law. It actually requires quite a bit of force to get it stretching to start with. Then it stretches very easily, and then it suddenly gets quite stiff again at the end. So if you draw a force extension graph for a rubber band or a balloon, what you actually end up with is a curved graph. It's steep at the beginning, flat in the middle, and then steep at the end. If you wanted to work out the total energy stored in the piece of rubber when it's fully extended, unfortunately there isn't a nice easy formula to use. You would have to look at the graph of force against extension and do what we've done before with previous graphs, which is work out the area underneath the line, and that will give you the work done stretching to that particular extension. One thing to note also, interestingly enough for rubber, is when you release the force, okay, yes, it does go back to its original length. So stretched, released, it goes back to its original length. However, if you look at the graph of force against extension, it doesn't follow the same curve going back. It actually follows a line that's lower than the line where it went out. And if you worked out the area under that line, it would actually be a smaller area below the unloading curve as you have under the loading curve. Now, why this difference? Well, the area under the unloading curve is actually the energy you get released back again when the piece of rubber goes back to its original length. Now, that's clearly less than the amount of energy that was required to stretch it in the first place. So it could be that, I don't know, it may take 0.4 joules to stretch it to that length. And then when I release it, you only get 0.3 joules coming back again. Now, obviously, that would seem to disobey the law of conservation of energy because we've lost a certain amount of energy. The solution to that is that energy gets retained by the rubber in this case. That's why it goes down on a different unloading curve. The energy gets retained by the rubber because the molecules that the rubber is made of, the long sort of chain polymers, they vibrate as they coil back up again. So some of the energy gets stored as heat energy. So some of the energy, rather than being returned directly when the rubber de-expands, it's actually stored in the rubber as heat energy. You also, if you remember, I did show you a curve for polythene as well, the stuff that plastic bags are made of. Rather than going back to its original length, polythene, when it's stretched, will stretch back to a length which is longer than the original length. And it's a similar thing if you work out the areas under the loading and the unloading curve. There's a difference between the two, and that's because some of the energy gets stored as potential energy in the molecules when the polythene is unloaded. So the long chain molecules, they're originally coiled up, but when you stretch the polythene, the molecules get stretched out, and when you release the force, when you unload the polythene, the molecules do not coil back up again like they did originally. They stay in a slightly uncoiled position, which means they have more potential energy stored in them. So some of the energy again is retained by the material, and you can see this from the difference between the loading and the unloading curves. But most of the questions you will get on this will be for a straightforward Hooke's law situation where you've got a spring or a wire and force is proportional to extension, and then you can just use the energy stored at any particular extension is a half K times delta L squared. Very easy to use. Okay, so that's energy stored in a material. The other small bit I needed to teach you tonight was the definitions of stress and strain. Now, why do we have to define these quantities? Well, if we take a wire and we look at Hooke's law, we can define the spring constant as the ratio between the force and the extension. The spring constant is F divided by delta L. Now, it should be fairly obvious to you that actually the spring constant doesn't depend only on the material that the spring or the wire is made out of. For instance, if we take two identical wires, but one of them is double the length, and we put the same force on the end of the wire that's double the length, it will extend twice as much. It will extend double the distance, which means that the spring constant will actually have half the value. In other words, the wire will be less stiff. It'll have a spring constant half the value of the shorter wire. Similarly, if you have two identical wires, but one of them is twice the cross-sectional area, so twice the thickness of the original wire, that wire, when you extend it with the same force, will only extend half as much. So the stiffness constant, or the spring constant of that wire, will actually be double the original wire. So defining the spring constant through Hooke's law, actually it gives us a number that doesn't just depend on the material, it does depend on the length and the cross-sectional area of the material. Now what we're going to look at in the next lesson is something called Young's modulus, which is basically a property purely of the material, and it's defined by looking at the ratio between stress and strain rather than force and extension. So stress and strain are numbers that we use instead of force and extension to look at this more sort of generalized form of Hooke's law, if you like. And stress is defined very simply. It's just the force, or the tensile force, divided by the cross-sectional area. So its unit is the same as the unit for pressure. It's newtons per square meter, or the Pascal. And that's how you work out stress. Strain is what we use instead of extension. Strain is the proportional extension of a material. So it's the extension divided by the original length. So if a material was to extend by 50%, then the strain would be 0.5. because the extension divided by the original length would be 0.5. If a material extended by 10%, the strain would be 0.1. If a material doubled its length, then the strain would be 1. So it's the extension divided by the original length, which doesn't have any units because it's just a ratio of two lengths. So those are two quantities that we need to define in order to go on to the next section, stress and strain. Pretty straightforward, but of course they're not terms that you will have come across before. They're not taught at GCSE, so it's important we understand how to calculate them. The most common mistake people make when calculating stress is with units. The reason being, of course, that if you're doing a wire, the cross-section of a wire is very small. It's usually in millimeters. And when you work out stress, you've got to divide the force by the cross-sectional area, not in millimeters squared, but in meters squared. So you've got to remember that if you've got 1 millimeter squared, it's not actually 10 to the minus 3 meters squared, it's 10 to the minus 6 meters squared, because it's the square of a millimeter and not just a millimeter. So people can fall up sometimes on doing unit conversions when you're working out stress, but it's something that at A level you should be pretty clear about how to do. Okay, so that's the work you've got to do this week. I'm going to give you some notes on it, and you're going to have some homework to do, and I would like it to be completed, if possible, by Sunday night at 6 o'clock. If you have any questions, do not hesitate to email me about them. Okay, just because we're not in school doesn't mean you can't seek out help and ask for help. Just remember that it is important that we don't get behind on these topics, particularly for you guys in the sixth form. We do have a very full curriculum next year, assuming that we're back in September. It's important that this term we keep ahead as best as we can and we don't slide behind. Okay, that's it. Thank you very much, and I hope you have an enjoyable rest of the week. Thank you.